What if I told you that somewhere out there right now intelligent life could exist, observing its own sky, asking the same question we do, are we alone? And yet, despite decades of searching, we have found nothing. So where's everyone? The answer is stranger, more profound, and more shocking than most people realize. Imagine standing on a quiet night on Earth, looking up at the sky, and realizing that the stars you see are not just points of light, they are suns, each potentially hosting their own planets, their own possibilities for life. Our galaxy alone contains hundreds of billions of stars, and there are estimated to be over 100 billion galaxies in the observable universe. That's an almost incomprehensible number of suns, each a nuclear furnace, each potentially surrounded by planets where life could take hold. Even if life arises rarely, the sheer scale of the universe implies that somewhere life must exist. And yet, when we scan the cosmos with our telescopes, listen with our radio antennas, and search for any sign of intelligent communication, we find silence. This paradox challenges everything we assume about life, intelligence, and the probability of encountering other civilizations. The immensity of the universe is both awe-inspiring and deeply humbling. We are a tiny speck on a small planet orbiting a medium-sized star in a galaxy among billions, and yet, the possibility that we might be alone is profoundly unsettling. It forces us to grapple with the tension between statistical probability and observational reality. Statistically, intelligent life should exist elsewhere, but observationally, the cosmos remains eerily quiet. This contrast is the first piece of the puzzle in understanding why the question, "Are we alone?" is far more complicated than it seems. The next layer of this inquiry comes from the Drake equation, a tool devised to help us think about the probability of intelligent life elsewhere. The Drake equation doesn't give a definitive answer. Instead, it provides a framework for understanding the factors that influence the development of communicative civilization. It begins with the rate of star formation in our galaxy, which establishes how many potential suns exist over time. Then it considers the fraction of those stars with planets, the fraction of planets in habitable zone where liquid water can exist, the probability that life actually arises on such planets, the probability that life evolve intelligence, and finally the probability that intelligent civilizations develop technology capable of communication. Each factor introduces uncertainty, and yet, even conservative estimates suggest that the galaxy should be teeming with life. What the Drake equation forces us to confront is not just the likelihood of life, but the incredibly delicate balance of conditions required for intelligence to emerge. It transforms the abstract question of extraterrestrial existence into a series of measurable variables that are grounded in astrophysics, biology, and planetary science. The equation highlights that the presence of life is contingent upon a chain of events from stellar formation to chemical evolution that are statistically improbable, but physically possible on a cosmic scale. Each variable represents a doorway to discovery, identifying exoplanets in habitable zones, studying extremophile on Earth, understanding the mechanisms of abiogenesis, and tracing the evolution of complex intelligence. The Drake equation is, in essence, a map of the unknown guiding our search for company in the universe while simultaneously emphasizing how much remains mysterious. It underlines a paradox. The universe is vast enough to almost guarantee life somewhere, yet our detection of it has remained elusive. The silence we perceive is not evidence of absence. It is a reflection of the limits of our observational capabilities and the profound distances and timescales that separate us from potential neighbors. In contemplating the immensity of the cosmos alongside the structure of the Drake equation, we begin to grasp the scope of the mystery. The universe could be teeming with life, yet remain silent and invisible to us, leaving humanity suspended in a cosmic dialogue where the other participants may be unreachable, undetectable, or fundamentally different from our own expectations. The Fermi paradox presents one of the most profound and perplexing dilemmas in the search for extraterrestrial life. It is named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" When we consider the immensity of the universe, the sheer number of stars, and the likelihood that some fraction of those stars host habitable planets, it seems almost inevitable that intelligent life should have a reason elsewhere. Yet, despite decades of searching, we have encountered no definitive evidence of other civilization. This paradox forces us to confront a profound contradiction. The statistical probability of alien life is high, but the observational reality is one of silence. It is a contradiction that challenges our understanding of biology, evolution, and the development of technology. The Fermi paradox compels us to question every assumption we make about life beyond Earth. Perhaps intelligent life is exceedingly rare, perhaps civilizations destroy themselves before becoming detectable, or perhaps their modes of communication are so different from ours that we fail to recognize them. It is a paradox that is as much philosophical as it is scientific, compelling us to think about the very conditions required for life to emerge, survive, and communicate across cosmic distances. The silence we observe is not necessarily the absence of life. It may be a reflection of the vast scales of space and time, a cosmic delay between the emergence of civilizations and their detectability, or even the possibility that advanced civilizations intentionally remain hidden. The Fermi paradox, in essence, is a mirror reflecting our own expectations back at us, revealing both the limitations of human perception and the profound mysteries of the cosmos. A crucial factor that might explain the Fermi paradox is the vastness of cosmic distances and the concept of cosmic isolation. Even if intelligent civilizations exist throughout the galaxy, the spaces between stars are immense that direct interaction, communication, or travel becomes extraordinarily challenging. The nearest star systems are several light years away, meaning that even signals traveling at the speed of light would take years to reach us. Consider that the Milky Way galaxy itself is over 100,000 light years across. A civilization in a distant corner of the galaxy might be sending out signals right now, yet those signals may take tens of thousands of years to reach Earth, and by the time they do, the civilization that sent them could have evolved, changed, or even disappeared. Cosmic isolation highlights a sobering reality. The universe could be filled with life, yet intelligent species may exist in isolation, incapable of detecting or interacting with others. The challenges are not only spatial, but also temporal. Civilizations may rise and fall on timescales much shorter than the communication times required across interstellar distances. Humanity might be looking for life at a moment when other civilizations have already vanished or have yet to emerge. The scales of space and time involved are so vast that the concept of now becomes almost meaningless on a galactic level. The universe does not operate on human timescales. Civilizations could blink in and out of existence, separated by distances and durations that render interaction improbable, if not impossible. In this context, the silence we perceive is not evidence of absence, but a consequence of cosmic isolation and the limits imposed by the laws of physics. The Fermi paradox thus becomes less of a puzzle about the rarity of light, and more a reflection of the fundamental constraints imposed by the universe's size and structure. This cosmic isolation also implies that our expectations about alien civilizations may be inherently biased by our own experience. We imagine extraterrestrial life as contemporaneous, capable of broadcasting signals we can detect or using technologies we can comprehend. Yet the realities of the universe suggest otherwise. Civilizations may communicate using methods we do not understand, or they may be constrained to local star systems, unable or unwilling to traverse the vast distances required for interstellar travel. Even if probes, messages, or physical artifacts have been sent across space, the likelihood that they intersect with Earth at the right time and in a detectable way is vanishingly small. This perspective forces a humbling recognition. Our search is shaped by human-centric assumptions, and the universe may be teeming with life in form, scales, or methods entirely alien to our perception. Cosmic isolation, therefore, is not merely a physical challenge, but a conceptual one. It teaches us that the absence of evidence is not evidence of absence. It reminds us that the universe operates on scales far beyond our intuitive grasp. Our observational tools, while increasingly sophisticated, are still limited by these fundamental constraints. The search for life is, in essence, a needle in a cosmic haystack problem, compounded by the immensity of space and the relativity of time. The interplay between the Fermi paradox and cosmic isolation also illuminate the subtle ways in which life might exist yet remain invisible to us. Civilizations may exist in technological states or evolutionary stages that we cannot detect. They may have abandoned electromagnetic signals as a primary means of communication long ago, transitioning to methods that propagate energy differently, or they may intentionally avoid detection for reasons of self-preservation. Perhaps life is abundant, but intelligent life that reaches a detectable technological threshold is exceedingly rare. The Fermi paradox and cosmic isolation together suggest that our assumptions about detectability, technological progress, and civilization longevity need to be re-examined. We must consider the possibility that intelligent life is not absent, but our observational framework is insufficient to perceive it. This requires both humility and creativity. Humility in acknowledging the limits of our perspective, and creativity in devising new methods, instruments, and theories to probe the cosmos. We are, in essence, looking for answers in a way that presumes similarity to ourselves. When the universe may operate on principles that transcend our expectations, furthermore, cosmic isolation reminds us that even if contact with another civilization were theoretically possible, the practical barriers are formidable. Traveling even a fraction of a light year with current technology is beyond human capability. Communicating across distances of thousands of light years introduces not only delays of millennia, but also the risk that one or both civilizations might cease to exist before any exchange can occur. The vast distances create a natural filter that limits the scope of interaction, even if life is common. In this way, the universe enforces a kind of solitary existence where civilizations may bloom independently, isolated by both space and time. The silence we observe may therefore be less a paradox and more an inevitable consequence of the universe's scale. Life could be everywhere, yet effectively isolated, making the question, are we alone, simultaneously profound and frustratingly unanswerable. With our current observational capabilities taken together, the Fermi paradox and the concept of cosmic isolation provide a framework for understanding why, despite the high probability of extraterrestrial life suggested by the sheer size of the universe and the Drake equation, we have yet to detect any sign of it. They highlight a tension between expectation and observation, probability and experience, imagination and reality. These principles underscore the need for patience, rigor, and creativity in our search for life. The universe may not be silent because it is empty. It may be silent because it is vast, isolating, and operating on scales that challenge our understanding. The questions posed by the Fermi paradox and cosmic isolation are not merely scientific, they are philosophical, existential, and profoundly humbling. They remind us that humanity is small, our technology is young, and our perspective is limited. Yet, our curiosity drives us to seek answers in a cosmos that may never fully reveal them. The question of whether we are alone in the universe forces us to confront a possibility that is as unsettling as it is scientific. Fascinating, intelligent life may exist, but the conditions required for its emergence and survival could be extraordinarily rare. This idea is central to what is known as the rare Earth hypothesis. Unlike the optimistic view that life is common wherever conditions allow, the rare Earth hypothesis suggests that while simple microbial life might be relatively frequent, the evolution of complex, intelligent, and technologically capable organisms could be the result of a highly improbable series of events. Think of it as a cosmic lottery, where the winning ticket requires not just one or two fortunate circumstances, but dozens, all aligning over billions of years. Planetary stability, a protective magnetic field, a stable climate, tectonics to recycle carbon and regulate atmospheric composition, a large moon to stabilize axial tilt are just a few of the factors that contribute to making a planet truly habitable over the long term. On top of that, a planet must survive cosmic hazards such as asteroid impacts, nearby supernovae, and gamma ray bursts, all of which could sterilize life or prevent complex life from evolving. When you consider the improbability of all these factors coinciding perfectly, Earth begins to look less like a typical planet and more like a remarkable, rare anomaly. This perspective forces a humbling realization: intelligent life may exist, but the universe may not be teeming with civilizations as we often imagine. The silence we detect, then, may not be a puzzle of observation, but a reflection of the extreme rarity of circumstances that allow for advanced life to exist at all. The rare Earth hypothesis also prompts us to consider the fragility of life once it arises. Even if a planet has the right conditions, the emergence of intelligence is not guaranteed. Evolution is contingent, unpredictable, and often shaped by random events. Mass extinctions, climate fluctuations, and stochastic environmental changes can erase progress toward complexity at any time. For instance, the asteroid impact that led to the extinction of the dinosaur allowed mammals, and eventually humans, to rise to dominance. Without such specific events, the trajectory of evolution could have been radically different. This highlights a profound lesson. The existence of intelligent observers on a planet is not simply a product of habitability, but of an extraordinarily intricate sequence of chance, events unfolding over geological timescales. In this sense, Earth may be the rare exception where a series of fortunate cosmic and planetary circumstances converged perfectly to produce life capable of asking, are we alone? This rarity challenges our assumptions about abundance and commonality in the universe. It suggests that despite the vast number of planets, intelligent life may be so uncommon that detecting it becomes a monumental challenge. The universe, expansive and ancient as it is, might still appear silent because the conditions that create beings capable of communication, technology, or interstellar signaling are exceptionally unusual. Every planet may host life in some form, but the leap from microbial existence to civilizations capable of exploring or communicating across the cosmos may be the cosmic bottleneck that explains our observational isolation. Closely tied to this is the concept of the Great Filter, which posits that somewhere along the chain from prebiotic chemistry to a technologically advanced civilization, there exists a stage that is extraordinarily difficult to surpass. The Great Filter could lie behind us, meaning that the evolution of intelligent life is incredibly rare, and we have already passed the improbable hurdle. In this case, humanity might represent one of the few instances in the galaxy where conditions aligned and we successfully navigated the filters that prevent most life from reaching intelligence or technological capability. On the other hand, the Great Filter might lie ahead of us. Perhaps civilizations inevitably self-destruct once they reach a certain level of technological sophistication through nuclear war, environmental collapse, or unchecked artificial intelligence. This possibility is unsettling because it suggests that the absence of detectable extraterrestrial civilizations could be a warning rather than reassurance. The Great Filter reframes the question of cosmic loneliness. The silence of the universe may not reflect absence, but the existence of obstacles so profound that very few, if any, civilizations survive long enough to make their presence known. It is a sobering thought, reminding us that intelligence and technology are not guarantees of longevity, but delicate achievements that may be as rare as they are remarkable. The concept of the Great Filter also invites reflection on the responsibility and fragility of human civilization. If the universe is silent because other civilizations failed to navigate the filters of survival, then humanity may be at a critical juncture. We must consider not only the physical and biological challenges to our survival, but also the technological, ethical, and societal choices that determine whether we endure. From climate change to nuclear proliferation, from artificial intelligence to resource management, the decisions we make today may determine whether we pass through our own Great Filter or join the multitude of civilizations that perished before achieving interstellar visibility. The cosmic silence becomes a mirror, forcing us to confront our vulnerabilities and the responsibility inherent in the intelligence that allows us to ask these questions in the first place. The universe does not wait for our answers. It operates according to its own laws, indifferent to human concerns, yet it is precisely this indifference that makes survival so extraordinary. Recognizing the potential existence of the Great Filter challenges us to cultivate resilience, foresight, and wisdom if we hope to persist as a civilization capable of observing and engaging with the broader cosmos. Furthermore, the interplay between the rare Earth hypothesis and the Great Filter underscores the delicate contingency of existence. Even if the universe is replete with planets and stars, even if life arises frequently at a microbial level, the combination of rare planetary circumstances and existential filters may mean that intelligent, technologically advanced civilizations are few and far between. This framework helps to explain why, despite the statistical likelihood of life elsewhere, our instruments detect only silence. The universe may not be devoid of life, but it may be sparsely populated with beings capable of sending detectable signals. exploring distant star systems, or surviving long enough to reach interstellar prominence. This perspective is simultaneously humbling and inspiring. Humbling because it places humanity within a vast cosmic context, highlighting the improbability of our existence. Inspiring because it emphasizes the preciousness of life and intelligence, where they do occur, offering motivation to protect, nurture, and extend the longevity of our civilization. The universe is a vast stage on which the emergence of intelligent observers is a rare and fragile performance. And our presence here is a reminder of the extraordinary improbability that life, intelligence, and technology can arise at all, even more profoundly. Considering the rare Earth hypothesis alongside the Great Filter invites reflection on the methods we use to search for extraterrestrial life. Traditional approaches like scanning for radio signals may be limited by the rarity of civilizations, their distribution across vast distances, and the possibility that they self-destruct before leaving detectable traces. It challenges us to expand our understanding of what life could be, where it might exist, and how it might communicate. Perhaps life is thriving in forms and locations that we cannot currently observe or perhaps advance. The civilizations choose modes of communication that are undetectable by our current technology. These considerations push the boundaries of scientific inquiry, encouraging interdisciplinary approaches that include astrophysics, astrobiology, planetary science, and even philosophy. The interplay of rarity, survival challenges, and observational limitations creates a landscape in which the absence of evidence becomes an invitation to innovate, explore, and reimagine our strategies for understanding life beyond Earth. Ultimately, the rare Earth hypothesis and the concept of the Great Filter compel us to confront the profound question at the heart of the search for extraterrestrial life. Not only why we have not found it yet, but what its absence or presence reveals about the fragility, contingency, and preciousness of our own existence. They illustrate that intelligence is not merely a product of habitability, but of extraordinary luck, delicate timing, and the navigation of obstacles that may be as formidable as the vast distances of space itself. This perspective challenges our assumptions, inspires caution, and deepens our appreciation for the singularity of our situation. In a universe of staggering scale, where life may be common at its simplest levels but rare in its complexity, humanity stands as both observer and participant in a cosmic drama that is as humbling as it is awe-inspiring. Even if intelligent life exists elsewhere in the universe, one of the reasons we might not have detected it is because we are simply looking for the wrong signals. Humanity has historically assumed that extraterrestrial civilizations would communicate in ways we can perceive through radio waves, lasers, or other forms of electromagnetic radiation. Yet this assumption may reflect more about our own technological history than the behavior of other civilizations. A species millions or billions of years older than ours might have long abandoned such primitive methods in favor of communication technologies beyond our comprehension. They could use neutrinos, gravitational waves, or quantum entangled particles, modes of interaction that are effectively invisible to us. Even within our own technological context, we see how quickly our communication methods evolve. The radio signals we broadcast today may be unreadable to humans just a few generations from now, replaced by fiber optics, satellites, and encrypted networks. Now imagine civilizations that have persisted for millions of years. Their broadcasts could be so alien in form, timing, and frequency that we wouldn't recognize them as signals at all. This possibility highlights a fundamental limitation in our search for extraterrestrial intelligence. We may not be alone, but our observational tools, conceptual frameworks, and assumptions about technology create a kind of perceptual bubble, preventing us from detecting what is actually out there. It is a reminder that silence does not necessarily equate to absence, that our understanding of life and intelligence must expand if we hope to interpret a universe potentially teeming with unseen complexity. Moreover, even if we consider civilizations that do attempt to communicate using forms we might detect, the timing problem creates another formidable barrier. Civilizations may rise and fall across cosmic timescales, and the universe is over 13 billion years old. Humanity has existed for a fraction of that time, and our radio and television signals have only been propagating into space for about a century. The likelihood that two civilizations exist simultaneously, have overlapping technological windows, and are capable of detecting one another is exceedingly small. In essence, even civilizations that do communicate may be separated not just by light years, but by millennia, resulting in a temporal mismatch that makes detection unlikely. The universe, in this way, enforces an invisible filter of timing. Civilizations could blink in and out of existence without ever intersecting in a meaningful way. The consequence is that the silence we perceive might be less a statement about rarity and more a reflection of the incredible challenges of aligning existence, technology, and opportunity across vast cosmic distances and epochs. It teaches us humility, forcing us to recognize the limits of human perception in a universe that operates on scales far beyond our everyday experience. Compounding these challenges is the possibility that life elsewhere in the universe may not resemble anything we recognize. Our search has been largely shaped by Earth-centric assumptions. We look for planets with water, stars like our sun, and biochemistry based on carbon. Yet life could take forms utterly alien to our understanding. It might exist in environments we consider extreme within the clouds of gas giants, beneath the icy crusts of moons, or even in forms that do not rely on carbon at all. Silicon-based life, plasma-based organisms, or entities that exploit chemical energy in ways inconceivable to humans could exist. Right under our observational noses, this possibility suggests that we might be looking for the wrong signature. Expecting life to mimic our own biochemistry and planetary conditions. The universe may be rich with forms of existence that challenge our definitions of life, intelligence, and civilization. And our inability to detect them is less an indictment of scarcity than of the narrowness of our perspective. To broaden our search, we must expand our imagination, develop new methods of detection, and consider life in forms that push the boundaries of biology, chemistry, and physics. Considering these factors together, the limitations of our technology, the timing problem, and the possibility of life as we do not know it, we begin to understand why the question, "Are we alone?" remains unresolved. The silence of the cosmos does not imply emptiness, but rather reflects a universe operating on scales, mechanisms, and possibilities that dwarf human experience. Our observational tools are still primitive in comparison to the vastness of space and the sophistication of potential life forms. Civilization may be common, communication may exist, but it might not be perceivable with the instruments and concepts we currently employ. The universe, in this respect, is like a library whose books we cannot open, whose languages we cannot decipher, and whose authors may have long moved on or are operating on timescales beyond our comprehension. The challenge, then, is not only to look outward, but to expand our conceptual horizons, to question assumptions, and to imagine the unimaginable. We are explorers of knowledge, but our map of the cosmos is still incomplete, and much of what might exist remains hidden, waiting for our understanding to catch up with reality. This contemplation also carries a philosophical weight. The silence of the universe challenges our assumptions of centrality, uniqueness, and inevitability. Humanity, for all its intelligence and technological achievement, exists in a cosmos that does not prioritize life, awareness, or comprehension. The vast distances, alien technologies, and unknown forms of life remind us that existence itself is fragile, contingent, and improbable. We occupy a small window in space and time, and the very fact that we are here to ask the question is itself remarkable. By grappling with the possibility of life that is undetectable or fundamentally alien, we come to appreciate the delicate balance that sustains our own existence. Our survival, our understanding, and our civilization are contingent upon recognizing and navigating a universe that is both incomprehensibly large and indifferent to our presence. The challenge of cosmic perception is a mirror reflecting our limitations and our ingenuity, compelling us to think not just about the stars, but about what it means to be aware of them. Finally, the combination of undetectable signals and life as we do not know. It serves as a call to expand both our technology and our imagination. To detect extraterrestrial intelligence, we must innovate instruments that probe the cosmos in new ways. From neutrino detectors to gravitational wave observatories, and develop frameworks that allow us to recognize intelligence in forms radically different from our own. Scientific humility is essential. The universe may be alive in ways that are beyond our current comprehension. The absence of detectable signals does not diminish the probability of life. Rather, it challenges us to evolve our methods of inquiry, to embrace uncertainty, and to persist in our search despite the obstacles. It is a testament to the audacity of human curiosity that, in the face of silence and isolation, we continue to ask, to observe, and to imagine. Taken together, these considerations, limitations of detection, temporal and spatial isolation, and the possibility of life, fundamentally different from our expectations, paint a picture of a universe that may be full of life, yet remains silent to us. The absence of evidence is not evidence of absence. It is a reflection of the complexity, scale, and diversity of cosmic existence. The universe, operating on scales and in forms beyond human experience, may harbor civilizations, signals, and life forms that we cannot yet perceive. This realization is both humbling and exhilarating. Humbling because it highlights all limitations, and exhilarating because it means that the search is far from over. The mystery of whether we are alone in the universe persists, but with each technological advance, each new exoplanet discovered, and each broadened conception of life, we move closer to understanding our place in the cosmos. Humanity's quest to answer this question is itself a testament to our intelligence, curiosity, and resilience, a reflection of the unique capacity of our species to contemplate the stars and to wonder what might be out there waiting for us to notice. So, after exploring the immensity of the universe, the tantalizing probability suggested by the Drake equation, the silence highlighted, by the Fermi paradox, the isolating vastness of space, the rarity of Earth-like conditions, the dawning great filter, the limits of our detection methods, and the possibility of life as we do not know it, we arrive at a humbling truth: the universe may not be silent because it is empty, but because it is vast, complex, and operates on scales that challenge our perception. Life, intelligence, and civilizations may exist, but they might be rare, hidden, or fundamentally different from what we expect. And yet, the very fact that we can ask these questions, probe these mysteries, and search for answers is a testament to the extraordinary capabilities of human curiosity, imagination, and perseverance. In a cosmos that is indifferent to our existence, the quest to understand whether we are alone becomes an achievement in itself, a celebration of our capacity to wonder and explore. Thank you all for joining me on this cosmic journey, for letting curiosity guide you to the edge of understanding, and for daring to ask the questions that remind us how remarkable our place in the universe truly is. Keep looking up, keep questioning, and never stop exploring.